Welcome to the tutor. I'm Joey Monday and I will be your tutor for electrical machine 2. And on today's lesson, we're gonna do an introduction to DC machines. And then as well, we're gonna focus on the first part of electrical machine 2, which is a DC generator. So talking about introduction to DC machine, what is a DC machine? The basic function of a direct current. That's the first thing that we should note. So we are using a direct current to convert ether electrical energy into mechanical energy, or to convert mechanical energy into electrical energy. So when it converts electrical energy into mechanical energy, it's called to be a motor, because you convert a DC current into a mechanical energy, so we call it to be a motor. And when it converts mechanical energy into electrical energy, it's called DC generator. Okay, because here we are taking a mechanical energy into a DC electric current, and therefore we can say our DC machine can be used either as a generator or a motor. So one machine, our one DC machine, can be used either like a generator or a motor. But our study today will be focused on a DC generator operation. How does this DC machine operate as a generator? First of all, we need flux. And in order for us to induce or to produce flux, we're gonna need to have pole. And this pole can be either permanent magnesium or a electrical magnetic field or electrical field poles. Okay. So once we know that when we have a pole, we have two poles, north and south. Therefore, our flux always move from north to south. The second thing we need a conductor. We put a conductor in the magnitude flux. Third things, we need motion. If we come with a motion, like for instance, as we say, we are converting mechanical force into electrical force. Okay, so our mechanical energy will be this. Okay, so this will be our mechanical force, because we're gonna come with a motion that is rotational, and then when our conductor is rotating in the flux, it's going to cut flux. When this conductor is cutting flux, there will be an induced EMF across it, so that when you come with a voltmeter, we're gonna measure a specific voltage. So that's how our DC machine operates as a DC generator. And therefore we're going to look at the construction. On the construction, we have our main frame, we have the main pole, we have the pole shoes, air gap, field winding, shaft, commutator, armature core, and as well armature slot. So we're going to have a look on each component or part of our DC machine to understand what is the purpose of each component. And therefore, the first thing, the part, we have a mainframe, starter or yoke. By definition, is the outer part of a DC machine, is made out of cast iron for smaller machine. So this part, the outer part of our generator, it's the mainframe. Okay, and therefore, why is the outer part of the machine made out of cast iron? That is a question that can come back to you, and the answer is that for physical protection of the machine, and then to provide housing for the pole, and as well to provide low reluctance for the magnetic field to flow. That's why this outer part of the generator is made out of cast iron. And then when we talk about pole, we are doing reference to this our pole. We have there a pole, we have a pole, and then we have a pole, so it provides us housing to pole. That's the reason why we have our outer part mainframe made out of cast iron. And then when you talk about pole or pole coil, basically when you look here, this is a pole. Okay, so we have a pole shoes. Our pole shoes will be this. It's made out of thin lamination sheet stacked together using the hydraulic press. So when you talk about lamination, it's like, see those small pieces that stick together to make our pole. And the reason why they are laminated is the reason why they are laminated is because of reducing the eddy current losses. Okay, I'm gonna explain more about the eddy currents in the coming video, where we are going. And then as well, we have the purpose of a pole. The purpose of the pole is to support field winding. The purpose of this pole is to support field winding, and our winding, this will be the winding. Okay, so this will be the winding, as you say, they say field coil. Okay, and then to provide low reactance to the path of the magnetic field. And then as well, we have our field coil are made out of copper conductor, and the purpose of it is to serve to excite the machine when the current pass through it. So we all know that when you have a conductor and they are turned together like this, it becomes like a coil. If the current flow through it, there will be a magnetic field that's gonna be generated around this conductor. Okay, so you have a conductor which is a coil. When the current go through it, there will be a flux that's is going to be generated, produced around our conductor. Okay, and therefore we're gonna have a look on the armature, which is the third part of our machine. This is our armature. Okay, all of these components on the armature are part of our armature, and we call it a rotor because it's the rotating part. So all of these components on our armature, they have made our rotor. Okay, so it's here that conversion between mechanical and electrical force occur. Okay, so the conversion between from mechanical to electrical, it occur there. Okay, rotor slot are the punch to accommodate coil and conductor. So as you can see, there is a slot here. A slot is like a small gap, so you're gonna come with a conductor, you lay it inside the slot. So the number of slots equal to the number of coil, and it's equal to the number of commutator. Okay, our commutator, this is our commutator here. This part here is our commutator. As it shows, you have a commutator. Okay, and therefore you have a type of winding that can be used on this slot. You have a lap winding. Lap winding is the same as C is equal to 2P. So when you read the problem and they say lap winding, the value of C, the number of conductor will be equal to 2P. P stands for number of pole. Okay, so you're gonna see how to use it more when we're gonna be doing tutorials. Okay, and then this is the type of winding when we talk about lap winding. And then you have another type of winding, which is wave winding. Our number of conductor will be equal to 2C. Okay, and then this is the type of wave. That's how we do those winding in the rotor. And therefore you're gonna have a look on our commutator. They are cylindrical shape. Okay, so you can see this is basically a cylinder. Okay, and draw copper segment isolated from one another. Can you see? So it's gonna have some segment here around this cylinder. Okay, and they are made in copper. Okay, So the purpose of a commutator, it serves to collect a collection point. So we collect our current from the commutator, okay, and then it's helping to do a rectifier. It's like a mechanical rectifier, converting AC to DC current, okay. And then the fifth part that we are going to have a look is our brushes, okay. Our brushes, as you can see from this commutator, our brushes are here. What are the purpose of those brushes around our commutator? Okay, so let's have a look on them and see what is the purpose of the brushes. Brushes, we use them as their purpose basically is to collect the current from the commutator. So as you can see, this is our commutator. We have our commutator here. So our brushes is to collect the current from the commutator, and then in a picture, physically, that's how they look. Okay, they are rectangular shape house in brushes holder and are made out of carbon or graphite. Tension spring aids, tension spring, those are the spring, because when the motor is rotating, sometimes it can be jumping on, and then those springs are just there to make sure that those up and down it's made well. Okay, flexible pink tie made out of copper. Okay, and then the purpose of these brushes is just to collect the current from the armature. That's the purpose of the brushes. We have some parts of the machine that we can now discuss, like the ball bearing, high balls, eld, shield, fan, shaft, feet, and crease nipple. Okay, and therefore in the equation, EMF equation for our DC generator, in order for power generation to take place, conductor, motion, and magnetic flux should be present, as we explained. It means that when the armature rotates in the magnetic field, conductor cuts flux and inducing the voltage in them. Therefore, our equation for the induced EMF is going to be given by 2 times the flux times Z and P times 60 over C. Remember the C we were discussing last time, the type of winding, and the type of winding that we have, we talk about lap winding, and then we say we have what? We have wave. So in the problem, when they state wave, you should know that with wave, I'm expecting to have C is equal to 2. When they say lap is going to be equal to what? 2P, ne? So the P is the number of per pole. Okay, so basically, as you can see, this formula is the same as this. Why so? Because 2 is a constant, okay, 60 is a constant, the number of pole doesn't change, and then the number of pole doesn't change, okay, and then as well the number of conductor Z doesn't change. Therefore all of these made our K constant, because those ones are constants. Once you have constructed the machine, the number of pole, the type of winding, the number of conductor doesn't change. Okay, so that's why you see this formula is same as that, because we have some constants in our machine construction. So as I say, we have a flux. P is a pole pair, number of conductor, and C is the type of winding, then as well as N the speed, which is rotation per minute. The speed can change, the flux can change. Okay, and therefore you have the type of excitation of our DC generator. We have the first one, which is the separately excited, and then as you can see from our construction, you have a armature, and then you have your field winding to produce a flux so that this conductor can cut those flux and induce a EMF. Okay, so that's basically what's happened. Okay, but with this one, what's happened, we're gonna need a battery. Okay, you're gonna need a battery to come and generate a flux, which is a magnetic electric flux. Okay, so we use a electrical current to induce a flux. Okay, so that's why you see this type of generation is less frequently used due to the need of an external source. So we need a source in order for us to produce flux in our DC machine. And then here we need to come with a battery across our winding, field winding, which means our poles, so that our poles can induce a electrical magnetic field. However, this type of winding is used for the magnetizing characteristic, so it's possible only when you have a separately excited. What happens if that characteristic that we are talking about? It's all about when you have a coil. We know that with a coil, it's a storage of current. Okay, so in order for me to store current, I need to come with a battery. Like when you used to do electrical one, you come with a battery. When you connect it across an inductor, the inductor will store current, so that when you come, you disconnect your battery across that conductor, there will be some current that will be stored in this conductor. So it's only possible when you do separately excited. Magnetization characteristic, as we explained, it's possible only when you start your magnetization characteristic. It's only possible when you excite your generator using a separately excited. So this will be our pole. So you come with an external source, and then you put the armature, no load condition, and then you bring a motion across that contactor, that armature. So when it's rotating, you have supply a current in the coil, there will be a flux that will be induced, there will be a flux that will be produced. When the flux is produced, this conductor is rotating, and then when this conductor is rotating, it's going to catch a flux. So once it catches a flux, there will be an induced EMF that is going to create a residual magnetism. A residual magnetism, it's only possible when you do a separately excited. Therefore, when you excite it, there will be a current that will be flow. The more it grow, this current to reach a new point, and then if you stop with turning the conductor, it's gonna decrease, but it's not gonna go from zero. Okay, it's gonna stop at a specific point. Okay, so this will be our residual magnetism, and it's possible only when you do a separately excited. Okay, and this residual magnetism, it's about 5 volts. So for instance, if you have your generator, if you go to measure across it, you will find that there's still some voltage that is stored inside them, and that voltage gonna be around 5 or less than 5 volts. Okay, so it's possible when you do a separately excited. And therefore we're gonna have a look on type of excitation of DC, and the most used and the most common one is a self-excited generator. Okay, and the self-excited generator is possible when the field winding is supplied from its own induced EMF, so you don't need an external source, and it's possible because of the residual magnetism. How do we generate a residual magnetism? First of all, you start with your separately excited, so that you can have some residual magnetism, and then now you can do a self-excited generator. It means you don't need any external source to come to connect on your field to generate the flux. No. Already you can just do some type of connection that it can start generating the current itself or induce a flux itself. Okay, and therefore, as we explained, what are the other type of connection that you can use? We have 3 types, and then we have the shunt. Shunt stands as parallel. Okay, and then you have the series generator, and as well your compound generator. This will be the 3 type of connection that you can do for a self-excited generator. It means we don't need any external source for us to produce flags. Once we produce flags, then we come with a mechanical source to rotate it and induce a EMF. So when we have a look on the self-excited generator, we're gonna have a look on the shunt. Shunt stands for parallel. Okay, so we're gonna have our field, which is our winding. You see this and that represents our field resistor. It means we need to excite the winding of the pole so that the pole can generate flux in our generator. So once we have generated that, we can come now with a mechanical force and then rotate it. Once you're rotating it, now there will be an induced EMF. Okay, so here what happens now is that you put your armature in parallel with your field, with your pole, with your field resistor. Okay, and therefore when you put the two in parallel, now when you start rotating your generator, or automatically without any external source, there will be a circulation of current. Can you see now that it has an ability for the current to circulate, and then now you can induce a EMF across the armature to measure. So there is no need of any external source. Okay, so as I say, they frequently use generator due to their simplicity and reliability. That's why we use a shunt. Okay, so what can be the advantage of this type of excitation? You have no excitation circuit, which means we don't need any external source like a battery to come to connect for us to produce flux. The flux it generates itself. And then beta speed control, we can do the speed control easily when you use it as a motor. The disadvantage of it, it's the prone to the armature reaction. Okay, we're gonna talk about the armature reaction, and then as well the load must be kept minimum when we are doing it connect as a shunt. Okay, because if our load is higher, if our load here is higher, what will happen? There will be less current flowing here, but the maximum current will be flow there. The more current we have, the more it's going to affect our induced EMF. Okay, but we're gonna discuss about it more deeply when we're gonna start doing some exercise. And therefore, another type, you have a series generator. With a series generator, it's all about connect your field in series with your armature. So the way it did, you come with a positive. This is a positive. This is connecting series with the armature. Okay, and therefore, once you connect like this, you come now with a mechanical force to rotate it. Okay, but with this series circuit, there is no way to start it without any load, which means at the beginning already you need to have a load so that there will be a flow of current, because without a load there won't be any circulation of current. Can you see that? So once you have connected a load, you see that now the current can flow. Without a load there won't be any flow of current. If there is no flow of current, there won't be any flux that will be generated or an induced EMF. Okay, so the advantage and disadvantage of this advantage is that it can be used as a constant current source. Disadvantage is that no excitation at higher load. Okay, unstable at variable load, lack of speed control. Okay, and then we're gonna have a look on another type, which is a compound generator. By compound we mean we combine the two. It has the advantage of both series and shunt. We combine the two so that we can make something that is close to percussion. Okay, and therefore we have two types. The first one is a long shunt, and then the third one is gonna be a short shunt. Okay, so what happened with this long compound, it's all about you have a series winding and then you have a shunt winding, so you can connect them either in a long shunt or in a short shunt. A short shunt, this will be the configuration. Long shunt, that will be a configuration. Okay, so we say this, it has an advantage of both, but what can be the disadvantage of this type of connection? Okay, because there is no perfection in electrical engineering. Okay, so therefore, as we say, a shunt path provides the necessary flux. In long shunt, the series winding control most of the flux. So the disadvantage of this is going to be the cost. The cost of this generator due to two coil, because the two coil gonna require more copper. Okay, and then as we said, I mentioned something about the armature reaction. What is the armature reaction? The armature reaction is the effect of the magnetic field step up by armature current under the distribution of flux under the main pole. Okay, so for instance, you have this pole. This pole, as we said, in order to excite them, you need to have coil connected across it, so that this coil is going to generate a flux. So this main pole generates a flux. Okay, and it's called to be a main flux. Okay, but remember that a armature also is a conductor. So if there is a conductor, we say any conductor that is coiled, okay, there will be a flux generate across it. Okay, so we have a generation of two flux: the main flux from the pole and the flux from the armature. Okay, so the two, they are going to, and in from electrical one, flux never interact each other. So the two flux are going to give a demagnetism main flux. Can you see? So it's gonna give a distortion. Can you see? So the flux want to be straight, as it shows from the beginning here. We're gonna have a distortion of flux. The flux will move a bit like that. So this can damage our generator. So in order for our generator to operate well, we need to do the correction of our armature reaction. How do we correct the armature reaction? First of all, shifting the brushes from geometric neutral plane to magnetic neutral point. Okay, so geometric neutral point is this geometric neutral point. So we need to shift from geometry to magnetic neutral point. So this will be our magnetic point. Okay, therefore you come, it's like the brushes used to be there, our collection of current was there, now we shift it to this point. Okay, and then another way to correct the armature reaction is another way to correct the armature reaction is to connect the compensating winding to counter the effect of the armature reaction. So we're gonna add a compensating winding in our pole. Okay, this will be our main winding, but we're gonna add a compensating winding, and this compensating winding is going to be connected in series with the main winding of our pole. Okay, another way to correct the armature reaction is to connect an interpole instead of the armature conductor. Okay, so we have the main pole. Will be our main pole. Now you come with additional pole in this, so that they are going to generate flux or in this direction, while the main pole is doing in this direction. Can you see? So this is going to correct the distortion as well. Okay, so an interpole, just an additional pole to correct the armature reaction. And therefore, we're going to have a look on the efficiency. As you know, it's always the P out over P in. But in the case of a DC generator, what is our P out? Our P out is electric power, but the P in is mechanical, because we are coming with a mechanical energy into electrical energy. So that's what the generator stands for: mechanical into electrical, the conversion from mechanical energy into electrical energy. And therefore, this is another way to calculate your efficiency. Then you have this formula as well, and then you have the power losses in the machine, because remember, in electrical engineering or in engineering, nothing will be perfect, but can tend to perfection like 99 or 98%. Okay, and therefore what can be the losses in our DC generator? First off, you have a copper losses due to the conductor. Okay, so you have a losses due to the armature winding, brushes, resistance, fields, winding, and as well external resistance, because they are made out of copper. There can be losses as well in our generator. And then you have the core losses. This is due to the eddy current. So the core is more about the type of material we use. Okay, and then you have the friction losses. Okay, and then you have another type of losses, the stray losses, which is basically a mechanical losses. And then the first one is the armature reaction. It's also a losses because during that mechanical losses, due to the armature reaction, it tends to stop, or to the speed won't be that 100%, because the armature reaction is trying to block it. Okay, due to that distortion. And then you have a weakening of the. So there will be a practice test that I will upload on the website. You need to go through it. Just try to do those exercises, which we are going to discuss from tomorrow, Monday, so that the feedback I will get from the practice test, and then on Wednesday I'm gonna make a video on how to start with tutorial question, or how to solve DC generator problem. So there will be a funny story about that practice test. I will tell you once you'll be able to solve those questions. So I will expect you to solve those questions, and make sure that you give me a feedback.